A huge thanks to Brian for sponsoring this video. Einen guten wünsche ich. Welcome back to another video. Today, something that I stumbled upon while teaching geometry in 8th grade while back. Do not worry, it's pretty interesting. It has been discovered before, obviously, like basically everything in elementary geometry. So it's nothing really new, you can find out about this, but it took me a while to actually find the term for it on the internet. It's the so-called inverse Pythagorean theorem. It's pretty cool. Maybe you have heard of it before, maybe you haven't. Stay tuned, it's quite interesting, at least in my opinion. By the way, the video has been sponsored by the wonderful people over on Brian, so if you're interested in online learning by doing, then they could be the perfect source for you. Wait until the end of the video, more information about them there, but now we are going to dive right in. So, how did I stumble across the inverse Pythagorean theorem? Well, it was while taking a look at the area of a right triangle, because there's actually two ways to get yourself a formula for the area of a right triangle. So how I teach it in school is, I tell my students, well, we can basically trace most of the regular shapes, be it the parallelogram, trapezoid, etc., back to a parallelogram too, and then consequently to not a square but the other thing, a rectangle. A rectangle, it's called a rectangle. I'm so sorry. Now we can do the same thing here. How can you get a rectangle out of this shape right here? We want to find a formula for the area of a triangle. Well, we could copy this very triangle and we can just glue it to the side. Meaning 2 times the area of this rectangle is going to be the area of this right triangle. Getting the area of a rectangle is pretty straightforward. In our case, it's just A times B. Meaning if we were to halve this area, we are going to get the area of a triangle. So area of the triangle is just A times B divided by 2. Now this is one of the ways to get yourself the area, and it's very easy, but this is just a special case which holds for right triangles. In a normal case, if you have a general triangle, you go about this a bit different. What you normally want to do is you want to duplicate the triangle, so the triangle that you got, in our case it's a right triangle, and then we are going to rotate it and glue it onto here, giving us a parallelogram in the process. So what you normally do is you take yourself your triangle, you copy it, giving you consequently 2 times the area once again, and a parallelogram in the process. Now if you were to put side lengths on here once again, you're going to have A, B and C here, obviously. But how are we going to get a rectangle out of this once again? Once you get to a parallelogram, it actually gets pretty easy. What you're going to do is you're going to put a height, the height on C, onto here. You're going to cut the whole thing and glue this part over here, giving you this shape in the process, which is a rectangle once again. What are the side lengths of the rectangle? Well, the side lengths are C and the height which is on C. You can actually repeat this process with all the other sides too in a general triangle. So what you're going to get is 2 times the area of this rectangle is C times the height on C, giving you overall, if you halve this, that the area of the triangle is C times the height on C divided by 2. You can go through this process too with A and the height on A and B and the height on B. But those are 2 equivalent formulations for the area of a right triangle. This is very important, and this is where it actually gets cool, because now we have a system of equations which we can set equal. The area of a triangle has 2 formulas, namely, by the transitive property of the equal sign as an equivalence relation, we also get that A times B divided by 2 is the same as C times HC divided by 2. And I'm going to refer to the height on C as just being the height, okay, inside of the right triangle. So I'm just going to write H from this point onwards. Now what you're going to notice is we divide on both sides by 2, so let's multiply both sides by 2, is that equal to 0, it's the successor of 1, so by definition is that equal to 0. Multiplying both sides by 2 gives us A times B is equal to C times the height. And this is where it struck me a tiny little bit, because, you know, we are inside of a right triangle. if we are inside of a right triangle, then the hypotenuse C, remember, can be expressed by Pythagoras as c squared is equal to a squared plus b squared times b squared. Oh my goodness. But we are not at the squared yet. It would be quite interesting actually if we could get ourselves the Pythagorean theorem into here. So what we're going to do is we're just going to square both sides. It doesn't change anything on the equation. We can equivalently do this. So a times b, but squared, is equal to c squared h squared. And now we can substitute c squared for a squared b squared. Putting the Pythagorean theorem into here, giving us that a squared b squared is equal to a squared plus b squared times h squared. And now we are going to make this a tiny little bit more interesting. We're going to divide both sides by a squared b squared. This is not equal to 0 because none of the squared parts are equal to 0 because we are in a triangle. So side lengths are defined strictly positive. And we are going to divide both sides by h. By the same argument, it's not equal to 0 because once we have certain side lengths, the height can also not be equal to 0 because it's a height standing on one of the sides. Giving us overall that a squared plus b squared divided by a squared b squared is equal to 1 over h squared. And now the very cool thing is that this right here is a fraction and the numerator is additive. So we can just drag it apart, giving us that a squared divided by a squared b squared plus b squared divided by a squared b squared is equal to 1 over h squared. And here's where the magic happens, and this is why it's called the inverse Pythagorean theorem. Those are going to be cancelled out, giving us in the process that 1 over a squared plus 1 over b squared is equal to 1 over the height on c squared. And this right here, that's the inverse Pythagorean theorem. And I think that is really cool because it's hidden in plain sight, going over the height. And it's basically the reciprocal form, kind of the regular Pythagorean theorem. It even includes c, at least implicitly in here, which is so cool. Did you know about this? I didn't know about this before I discovered it, but it's really, really cool. And one thing that should come immediately to your mind is, do there exist inverse Pythagorean triples? So remember, regular Pythagorean triples are when you got integer side lengths. For example, one of the most famous ones is the smallest possible Pythagorean theorem, where none of the variables in here is equal to 0 because then it wouldn't be a triangle anymore, is namely that a is equal to 3, b is equal to 4, and c is equal to 5, giving us that 16 plus 9 is 25, which is indeed 5 squared. That's a Pythagorean triple. And remember one thing about Pythagorean triples, namely that integer multiples of all those are also a Pythagorean triple. For example, a is equal to 6 and b is equal to 8 and c is equal to 10. This just follows directly from the Pythagorean theorem, because what we can do is, we can, for example, if we have 3 squared plus 4 squared is equal to 5 squared, what we can do is we can multiply both sides by 2 squared, for example, giving us 2 squared, 3 squared plus 4 squared times 2 squared is equal to 2 squared times 5 squared. And factoring out the squared on all of those is going to result in 2 times 3 squared plus 2 times 4 squared is equal to 2 times 5 squared. And you see, this right here is indeed a new Pythagorean triple, giving us 6, 8, 10 in the process, and so on and so forth. So you can generate in the regular Pythagorean theorem infinitely many Pythagorean triples from one given. Now I was wondering, does this work too with this constellation? But one thing we need to impose on this whole problem is that h is going to be an integer too. Otherwise it wouldn't be a Pythagorean triple in this sense. So let us try this out. And what I did is I was using the regular 3, 4, 5 triple. And then I went back to the original equation, namely that AB is equal to CH. If we were to plug all of this in, let us do it with numbers before we generalize this whole process. We're going to get with the regular Pythagorean triple, the smallest one, that 3 times 4 is equal to, well, 5 times h. Meaning, at the moment, 12 is equal to 5 times h. That's a problem, because immediately if we were to use this, we are going to get that h is equal to, well, 12 divided by 5, which is going to be, it fits 2 times into here, so 2.4. This is not an integer, at least not by my book. So how can we get, with a given Pythagorean triple, I didn't want to stop here because certainly we could get h to be an integer if we just multiply it by 5. Okay? How can we make 5 into h into an integer such that the Pythagorean triple is kind of preserved? This is what we want to try here. So multiplying h by 5, we are going to get that 5h is indeed an integer, namely 12. And remember, this is just basically getting back to this equation. It's just a times b in this process, or 3 times 4. But now we got a problem. What we did is we multiplied h by 5. But you can't multiply or put this 5h into here, because then the equality wouldn't be an equality anymore, because it would say 3 times 4 is equal to 5 times 5 times h, the original h. So what we can do instead is we could multiply this whole equation right here by 5, such that our h, our height, which we don't know yet, is an integer, but our equation, the original one, is going to be preserved. So what we're going to do is we multiply the whole thing by 5, giving us 5 times 3 times 4 is equal to 5 times 5 times h. So this right here is element of the natural numbers. That is good. All of the other stuff is also element of natural numbers. But we do not have a Pythagorean triple anymore with c included. Because now we have as a possible Pythagorean triple that 5 times 3, for example, so 15 squared plus 4 squared is equal to 5 squared. This obviously doesn't hold anymore. But how can we make it hold? Remember what I told you before. If we have a given Pythagorean triple, we can multiply each part by the same integer, and we get an equivalent Pythagorean triple out once again. In our example, what we did is we multiplied 3 by 5, giving us not a Pythagorean triple anymore in the process. But how about we multiply c and b also by 5, giving us 5 times the original one, resulting in a Pythagorean triple once again. And this is actually quite fortunate if you think about it, because we have this part right here, this is a, just multiplied by 5. We got b here and we got c here. 5h is an integer, but 4 and 5 are not yet in terms of a Pythagorean triple, so multiplying both sides by 5 is going to result, luckily, and this is really cool in my opinion, in 5 times 3 times 5 times 4 is equal to 5 times 5 times 5h. And this is really cool because 5 times 3, 5 times 4 and 5 times 5 is gonna give us an original Pythagorean triple by the thing that I told you before. I proved it a little bit. But also 5 times h, which is equal to 12, which is the same as our original cathetes multiplied together, is gonna be an integer too. Meaning overall, we are going to get an original Pythagorean triple and also an inverse Pythagorean triple in the process. Isn't that fucking cool? Like seriously, that is so cool. And this, in my opinion, is so much more interesting than regular Papa Pythagoras that we are used to, because we are dealing with fractions here and it gets a bit harder. But how can you generalize this process? What did we do here exactly? What was the thought process? Because there must be a way, obviously, to generalize this procedure to any other old Pythagorean triple that I give you. 8, 6 and 10, I think. 8, 6, yeah, 8, 6, 8 and 10 is also a Pythagorean triple. How can you get yourself an inverse Pythagorean triple out of this too? Let us define a little procedure. So let us suppose that a, b and c are an original Pythagorean triple. We are going to get our equation ab is equal to c times h. Now remember, if we were to solve this whole thing for h, then h is going to be a times b divided by c. And without loss of generality, we don't want to get too much into detail here, it's never going to be that case, at least in my opinion. We're going to suppose that this right here is not an integer. And even if it were, it really doesn't change the procedure. How can you get yourself an integer out of it? Well, we are going to substitute our h for h times c. so c times h, hypotenuse multiplied by h, is going to result in a times b, which is indeed an integer. So this right here, check. Now if we were to substitute our c times h into here, we are going to have a tiny little problem. The original equation is not going to be preserved. That was the problem that we got right here. 5h we can put it into here, because then 5 times 5 times h is going to be 3 times 4, which is not the case by the original definition of h. So what we need to do consequently is we can get rid of this problem by multiplying the whole original equation just by c, giving us that a times c, I'm going to write it like this, times b is going to be equal to c times h. C times h is the same as a times b, which is going to be an integer, which does make sense, because if you substitute for a times b, it's going to be just a true statement. Now we are at a point where a times c falls out of the picture when it comes to the original Pythagorean triple. But how can we get back to a Pythagorean triple? Well, by multiplying both sides by c yet again, because then we are going to get a multiple of the original Pythagorean triple. So multiplying both sides by c is going to result in a times c times b times c is equal to c squared times c times h. And this right here is going to be a Pythagorean triple, including an integer solution to our inverse Pythagorean triple. And this is the procedure that you're going to do. All you really have to do is you are going to multiply your original Pythagorean triple, for example 6, 8 and 10, by the hypotenuse. Meaning the new Pythagorean triple is going to be this right here is the hypotenuse, 60, 80, 100. And what is the height gonna be? Well, the height is gonna be c times h. But we don't know anything about h, apart from the nice little fact that c times h is equal to a times b. Meaning, our height that we are gonna have in this right triangle is gonna be 6 times 8. We are gonna use the original a times b. 6 times 8 is 48, which is indeed an integer. And then we are done. And I think this is really cool. That's a generalized procedure for a completely new problem that you maybe haven't heard anything about before. Let me know down there in the comments what you think about it, but I think that is really nice. And if you stumble upon something like this on accident, it's even more cool than that. And I hope I made your day at least a tiny little bit. And if you're interested in more things like trigonometry, algebra, playing around with equations and systems of equations, then Brilliant might be the perfect fit for you. Now, what is Brilliant? Brilliant, to put it short, is one of the best sources for learning online out there on the World Wide Web. And when I say it, I mean it. I use it on a regular basis. I use it to show trigonometry and also geometry in my classes. I use it to brush up on old topics that I have long forgotten about. And also I use it to learn something new for my personal studies. And this is really cool. I'm a studied mathematician and also a studied physicist. But I still find something over on their website, in their courses, that I am not yet familiar with. Something that I can learn about today. By using my phone, for example, or my laptop, I can use Brilliant on the go and learn something while sitting in a bus. Or maybe walking around in the park, thinking I could learn something about Markov chains today. Why the hell not? I'm walking in the park. Probability is probably something that I would like to learn right now. But all jokes aside, it's just really cool to use Brilliant. And don't take my word for it. Try it out for yourself by using my link down there at the top of the description, brilliant.org/flammablemavs. With it you're going to get 30 days free trial. Try everything out to your heart's content and then see if it's something for you and if you want to have a long-term relationship with their excellent courses. Then maybe make use of the link completely. Make clicky on the linky and get 20% off an annual premium subscription, which is a huge discount if you ask me. And also you're gonna have infinite access to everything which is there already and which is gonna come on a regular basis. They are improving on their courses from time to time, once per month and also all the time. And they are making it better by the day. And seriously, I don't know how you can make their courses better, but it just works. They kind of manage to give the user a better experience each update. It's just very cool. So try it out and support the channel this way. And if you did enjoy what you've seen today, why not make sure to subscribe to the channel too? I really liked what I did here today. That was a fun video. That was really a fun video. I really liked that. And also subscribe to Flammy's Wood, my woodworking channel, if you're so nice. And until the next video, I wish you guys a flammable day. See ya!